Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1997 publication by Elizabeth Blackburn and Carol Greider, alongside Kelvin Harley, in Scientific American, represents a masterful work of synthesis and scientific prognostication titled Telomeres, and Cancer. This article served as a definitive declaration to the wider scientific community, consolidating over a decade of pioneering research into a coherent and compelling narrative. It connected the esoteric biology of ciliated protozoans to the most fundamental questions of human existence, the mechanics of aging and the runaway proliferation of malignant cells. This essay will perform a deep, internal evaluation of the claims, arguments and evidence presented within that specific 1997 text, proceeding section by section to analyze the intellectual architecture of their thesis. The objective is to understand the work on its own terms, assessing the logical force and evidentiary basis of its propositions as they were articulated at that pivotal moment in molecular biology. Section 1, elucidating the fundamental dilemma of chromosome maintenance. The authors commence their argument by framing a profound biochemical paradox, what is now universally known as the interreplication problem. Their exposition of this issue is a model of conceptual clarity. They describe the mechanics of deoxyribonucleic acid, or DNA, replication, focusing on the established properties of DNA polymerase. The article explains that this enzyme synthesizes new DNA in a 5' to 3' direction and requires a ribonucleic acid, or RNA, primer to initiate the process. The leading strand of the DNA double helix is replicated continuously. The elegance of their explanation resides in their depiction of the lagging strand, which is synthesized discontinuously in fragments. The authors claim that upon removal of the final RNA primer at the very tip of the linear chromosome, there exists no upstream 3' hydroxyl group from which DNA polymerase can fill the resulting gap. Consequently, with each successive round of cell division, a small portion of the chromosome's end is irretrievably lost. The evaluation of this claim reveals its power as a narrative device. It establishes an unavoidable, mechanically determined fate of cellular decline. The evidence for this mechanism was well established in the molecular biology of the time, and the authors leverage this consensus to create an immediate sense of intellectual tension. They present chromosome shortening as a fundamental aspect of cellular life in eukaryotes, an inbuilt countdown timer whose existence demands a biological countermeasure if long-term genetic integrity is to be preserved. Their argument is entirely deductive, proceeding from the known characteristics of polymerases to an inevitable conclusion. This framing is crude. It posits a universal problem for which they are about to reveal an equally universal and astonishingly elegant. Section 2, the discovery of a novel ribonucleoprotein polymerase in ciliates. Having established the problem, the article pivots to its solution, recounting the discovery of the enzyme telomerase. The authors describe their foundational work in ciliate tetrahymena thermophila, a single-celled organism with a vast number of small, linear chromosomes, making it an ideal system for studying chromosome ends. The central claim of this section is the existence of a unique enzymatic activity capable of synthesizing new telomeric DNA onto chromosome ends, thereby compensating for the loss during replication. They detail the breakthrough experiment where a synthetic oligonucleotide bearing the tetrahymena telomeric repeat sequence, which is a repeating pattern of thymine-thymine duonine, was added to a cell-free extract. The observation was that this synthetic primer was elongated by the addition of more of the same characteristic repeating sequence. This claim is supported by the direct experimental evidence they present. The evaluation of this argument highlights its intellectual audacity. The authors proposed that this elongation was accomplished by a reverse transcriptase, an enzyme that synthesizes DNA from an RNA template. This was a remarkable hypothesis, as reverse transcription was primarily associated with retroviruses. Their subsequent claim that the telomerase enzyme itself contained an intrinsic RNA molecule that served as the template for the synthesis of the guanine-rich telomeric repeats was a profound conceptual leap. This section of the article effectively presents the discovery not as a serendipitous finding, but as the logical resolution to the paradox outlined earlier. The argument's strength lies in the simplicity and decisiveness of the described experimental results, which left little room for alternative interpretations. They had found the missing piece of the replication puzzle, an enzyme that actively rebuilds the chromosome ends. This section solidifies the central mechanism of their entire thesis. Section 3, translating the unicellular mechanism to human cellular aging. Article then makes its most significant analogical leap, connecting the biology of a pond organism to the process of human cellular aging. The authors introduce the established concept of the Hayflick limit, the observation that normal human cells in culture divide a finite number of times before entering a state of irreversible growth arrest known as replicative senescence. The pivotal claim of this section is that telomere shortening functions as the molecular clock that counts these cell divisions and dictates the onset of senescence. The evidence presented for this claim is primarily correlational. They cite studies demonstrating that telomeres in human fibroblasts, and indeed in cells of many somatic tissues, progressively shorten with each cell division and with the age of the organism from which they were taken. The evaluation of this claim must appreciate its status in 1997. It was a powerfully unifying hypothesis, providing a tangible, mechanical explanation for the abstract Hayflick limit. The authors argue with great conviction that this shortening process is a direct cause of cellular aging. The internal logic is compelling. If cells lose a piece of their chromosome with each division, and if this loss eventually reaches a critical point, then the cell must cease dividing to protect its essential genetic information. This transforms cellular aging from a passive, cumulative process of damage into an active, genetically programmed surveillance mechanism. The article's presentation of this idea is declarative and confident, positioning telomere dynamics as the central governor of cellular lifespan, while subsequent research would add significant layers of complexity to this model. The 1997 article presents it as a direct and primary causal relationship, a bold assertion that galvanized an entire field of research. Section 4, proposing telomere length as a mitotic clock for the organism, building directly upon the previous argument. The authors expand the scope from the cellular to the organismal level. This section posits the telomere hypothesis of aging, claiming that the finite replicative capacity of individual cells, dictated by telomere length, contributes to the aging of the whole organism. They propose that as cells in renewable tissues like skin, the gut lining, and the immune system approach their Hayflick limit, the tissue's ability to repair and regenerate diminishes. This leads to the functional decline associated with aging. The argument is again based on logical extension and correlation. They reason that an organism is only as robust as its ability to maintain its tissues, and this ability is fundamentally constrained by the replicative potential of its constituent cells. The evidence cited includes observations of telomere shortening in human lymphocytes with age, suggesting a potential link to the age-related decline in immune function or immunosenescence. An evaluation of this claim reveals both its intellectual appeal and its speculative nature at the time. The authors are careful to frame it as a contributing factor, a hypothesis, but the rhetorical force of the article lends it significant weight. It presents a beautifully linear and mechanistic vision of aging, where a molecular clock in each cell aggregates to a systemic, organismized process of decline. This vision has a certain parsimonious elegance, suggesting that at least one component of the complex phenomenon of aging could be traced back to the simple arithmetic of DNA replication. The intellectual contribution here is the construction of a plausible, testable framework linking the most fundamental level of molecular biology to the lived experience of organismal senescence. Section 5, identifying telomerase activation as a critical step in carcinogenesis. The article then presents its most clinically significant and perhaps most impactful claim, the intimate connection between telomerase and cancer. The central argument is that for a cell to progress to a state of malignancy, it must overcome the barrier of replicative senescence. It must, in essence, become immortal, the authors claim, but cancer cells achieve this immortality by reactivating the telomerase enzyme, which remains dormant in the vast majority of normal human somatic cells. By turning telomerase back on, cancer cells can maintain their telomeres indefinitely, allowing for the limitless proliferation that is the hallmark of cancer. The evidence presented for this claim is exceptionally strong and forms the core of the article's medical thesis. They report on surveys of human tumours, stating that significant telomerase activity is detectable in a very high percentage, something approaching 90%, of all cancers. Conversely, most normal, healthy tissues lack this activity. This stark differential is presented as a near-universal marker of malignancy. The evaluation of this argument must acknowledge its profound impact. It reframed cancer biology. Cancer was now understood as a disease that hijacks a fundamental developmental mechanism. The telomerase-positive cancer cell is one that has rediscovered the secret of the single-celled eukaryote, or the embryonic stem cell, the secret of endless division. The argument is powerful because it provides a common denominator for the vast majority of disparate cancer types. It suggests that despite their myriad genetic mutations, most cancers converge on the same solution to the problem of cellular mortality. This claim transformed telomerase from a biological curiosity into a prime target for therapeutic intervention. Section 6, envisioning a future of telomere-based therapeutics. In its concluding section, the article ventures into the realm of future application, making two major propositional claims. The first and more concrete claim is that inhibiting telomerase could be a powerful and selective strategy for treating cancer. The authors reason that since most normal cells lack telomerase activity, a drug that specifically targets the enzyme would have minimal side effects on healthy tissues. Such an inhibitor would reimpose the Hayflick limit on cancer cells, causing their telomeres to shorten with each division until they either entered senescence or died. This would effectively turn the cancer's own proliferative nature against it. The second, more speculative claim addresses the other side of the coin, the possibility of using telomerase to combat age-related diseases. They cautiously propose that a controlled, transient activation of telomerase in specific cell populations could potentially extend cellular lifespan, rejuvenate tissues, and ameliorate some conditions associated with aging. Evaluating these claims requires recognizing their differing levels of certainty. The vision of telomerase inhibitors for cancer therapy is presented as a direct and logical consequence of their findings, a clear path forward for drug development. The argument is methodologically sound and has indeed become a major focus of oncological research. The proposition regarding anti-aging therapies is framed with more intellectual caution. The authors implicitly acknowledge the immense complexity and potential dangers, such as an increased risk of cancer, that could accompany the artificial extension of cellular lifespan. This section demonstrates a keen awareness of the dual nature of their discovery. Telomerase is presented as both the key to understanding cancer's immortality and a potential tool, if wielded with extreme care, for enhancing cellular longevity. It is a Chanus-based enzyme. Our authors skillfully articulate both its threat and its In conclusion, the 1997 article Telomerase, and cancer stands as a landmark of scientific communication and a testament to the power of a unifying theory. A critical evaluation of its internal claims reveals an intellectual structure of remarkable coherence and persuasive force. The authors begin with a fundamental biochemical problem, present an elegant enzymatic solution discovered in a model organism, and then boldly extrapolate that mechanism to explain the core human processes of cellular aging and cancer. The chain of reasoning, from the end-replication problem to the Hayflick limit, and from cellular senescence to malignant immortalization, is presented as a nearly seamless logical progression. The evidence for each key claim, particularly the activation of telomerase in the vast majority of human cancers, was compelling and has been overwhelmingly substantiated in the subsequent decades, while the direct, linear model of telomere shortening as the sole driver of organismal aging has since been integrated into a more complex, multifactorial understanding. The foundational claims of the 1997 paper remain the bedrock of telomere biology. Its enduring significance lies in its successful articulation of a grand narrative, one that provided a generation of scientists with a clear conceptual framework and a set of testable hypotheses that have since yielded profound insights into health, disease, and the very nature of biological time.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.